You know, inside literally every single device you own, there's a tiny component that's basically a perfect one-way street for electricity. It's the silent gatekeeper that makes all modern electronics work. Today, we're going to pull back the curtain on that fundamental building block, the PN junction.
So, how in the world do you actually build something like that? A one-way street for electricity? How do you make sure current flows forward, but gets totally blocked if it tries to go backward? Well, the answer is this really elegant little device called a PN Junction diode.
All right, so to create this amazing one-way street, we start with a super common element, silicon. But we can't just use it plain. We need two specially prepared or doped versions of it. These are our key electronic ingredients. So on one side, we've got what's called P-type silicon. Just think of it as having a bunch of extra positive spaces, we call them holes, that are just waiting to grab an electron. And on the other side, you've got N-type silicon, which is loaded with extra free-roaming negative electrons. So basically, one side is desperate for electrons, and the other has a ton to spare.
Now for the fun part. What happens when you stick these two materials right up against each other? It is not a quiet meeting, I'll tell you that. The second they touch, there's this immediate, automatic, and absolutely critical reaction that happens right at that border, at the junction.
Let's break it down. Right away, those extra electrons on the N side see all those empty holes on the P side, and they just rush across to fill them up. As they meet and combine, they kind of cancel each other out. But here's the thing. This leaves behind these stationary charged atoms called ions that are now stuck in place. And the result? You get this barrier in the middle that has no free charges left to move around at all.
And this special zone, this no man's land, it has a name. The depletion region. It's called that because it's been depleted of any free-moving charges. It basically acts like a natural insulator, a barrier that just stops electricity cold right there at the junction. Now, this barrier isn't just a physical thing, it's an electrical wall. It actually creates its own tiny voltage, a built-in potential. And for silicon, which is what we use most of the time, this barrier is about 0.7 volts. So think of it like a locked gate that needs a key, and that key is exactly 0.7 volts of pressure to even start to push it open. So we've got this locked gate. How do we get any current to flow? Well, we've got to apply a little external pressure to force that gate open. And we do this by hooking up a battery in a very specific way, creating a condition we call forward bias. So here's what we do. We connect the positive end of a battery to the P side and the negative end to the N side. What this does is it starts pushing those positive holes and negative electrons toward each other, squeezing them right up against that central barrier. And all that pressure from the battery, it starts forcing the holes and electrons together, which in turn cancels out those stationary ions that made up the barrier in the first place. And as a result, that insulating wall, our depletion region, it starts to get thinner and thinner. It shrinks. And here it is, the magic moment. As soon as the push from our external battery gets bigger than that built-in 0.7 volt barrier, we've done it. We've broken through. The gate is officially unlocked and swung wide open. And with that barrier effectively gone, current can just flood through the junction with almost no resistance. The diode is now acting just like a piece of wire, a conductor. We have officially opened our one-way street for business. Okay, but what happens if we get sneaky and flip the battery around? This is called reverse bias. And as you're about to see, this is how we don't just lock the gate, we basically deadbolt it and throw away the key. So now we've reversed the battery. The positive end is pulling on the electrons from the N side, and the negative end is pulling on the holes from the P side. So instead of pushing everything together toward the middle, we're pulling them apart, away from the junction. And what does this do? Well, it uncovers even more of those stuck ions right at the junction, which makes our barrier, the depletion region, even wider and more powerful. We're essentially reinforcing the wall, making it an even better insulator than it was before. And with a barrier that wide and that strong, the main flow of current is just stopped dead in its tracks. I mean, for all intents and purposes, nothing is getting through. The gate is now double bolted shut. Well, I say nothing gets through. That's almost true. There is one tiny exception. Remember how each side had a majority of one type of charge? Well, they also have a few of the other kind floating around. We call those minority carriers. And the reverse voltage actually helps these very few carriers to sneak across the barrier, creating a teeny tiny leakage current. And here's a really fascinating detail. This tiny leakage current is incredibly sensitive to heat.
For silicon, for every 10 degrees Celsius jump in temperature, that little leakage current just about doubles. It's a tiny effect, for sure, but it's absolutely crucial for engineers who are designing really sensitive electronics.
So let's just step back and put it all together. We've just seen two completely different behaviors from the exact same device. All we did was change which way the voltage was pointing. That right there is the whole secret to our one-way street. You hook it up one way, in forward bias, it's a conductor. Green light, current flows. You hook it up the other way, in reverse bias, and it becomes an insulator, a brick wall. Current stops. It is a perfect solid-state switch with absolutely no moving parts.
So, yeah, just by controlling the direction of a little bit of voltage, we create this perfect electronic one-way gate. And this simple, beautiful principle is what lets us do everything from converting AC to DC in our phone chargers, to protecting delicate circuits, to building the fundamental logic gates that are the beating heart of every computer on the planet.
I mean, think about it. From this one simple component, we build transistors, then microchips, and eventually our entire digital world. It just goes to show you that the most powerful, world-changing technologies can come from the most simple, elegant physical rules. So the only real question left is, what are we going to build with it next?